All right, let's dive right into this explainer. Today, we're going to discover how to decode the entire physical world just by learning its fundamental language. So, welcome to our journey through the building blocks of reality.
Here's our roadmap for today. We're hitting the physics alphabet, unlocking dimensional formulas, distance versus displacement, the math of motion, and finally, graphing our progress. Let's get right to it.
Section 1. The physics alphabet. Fundamental and derived units.
So here's the crucial thing. Fundamental quantities, stuff like mass, length, and time, they stand completely on their own. They're the independent building blocks of the universe. You just can't break them down any further. But derived quantities like area and volume, those depend on the others. They're built by mashing those basic foundations together. It's literally like combining letters to make words. We combine fundamental units to express entirely new physical concepts. Just to put these units into a real-world perspective, keep in mind that 1 metric ton is exactly 1,000 kilograms. I know, it sounds super simple, right? But locking down these standardized conversions is literally the only way scientists from Tokyo to Toronto can collaborate without, accidentally crashing a multi-million-dollar satellite. And this perfectly shows how the SI and CGS systems translate into one another when we're measuring vast areas or volumes. Let's look at how these numbers actually behave. Since area is a derived quantity of length squared, 1 square meter isn't just 100 square centimeters. No way! Because you're squaring it, it scales exponentially up to 10,000 square centimeters. It's the same deal with volume. A single cubic meter balloons all the way to 1 million cubic centimeters. Getting a handle on this exponential scaling is absolutely vital for keeping your measurements dead-on accurate when jumping between dimensions.
Moving on to Section 2. Unlocking dimensional formulas. The grammar of physics.
By understanding the powers that these fundamental quantities are raised to, we actually unlock 3 incredibly powerful mathematical tools. With dimensional analysis, we can check if a formula actually makes physical sense. We can seamlessly translate one system of units into another, and this is the really cool part, we can derive brand new relationships between different physical quantities without running a single physical experiment. Pretty wild, right?
Now, what's genuinely fascinating here is that this master table is basically our ultimate Rosetta Stone. It perfectly maps out the general formulas, dimensions, and SI units for 11 core physical quantities. Take a really close look. See how every single complex derived quantity, from force all the way to pressure, ultimately just breaks down into M for mass, L for length, and T for time. And notice how work and energy share the exact same dimensional formula. It just perfectly exposes the hidden underlying architecture of physics.
And that brings us to the principle of homogeneity. This is the absolute golden rule of physics grammar. It states that only physical quantities having the same dimensions can be subtracted or equated. Basically, it ensures we never try to do something crazy like add mass to time or subtract length from volume. It guarantees that an equation is only physically valid if the dimensions on the left side perfectly match the dimensions on the right side.
All right, let's test our memory of that master table with a quick checkpoint directly from the syllabus. What is the dimensional formula of acceleration? Think about the definition for a second. It's the change in velocity over a specific period of time. So how on earth would we write that out using our M, L, and T grammar?
Well, if you guessed M0, L1, T-2, you hit the nail on the head. You are perfectly in tune with our dimensional grammar. Acceleration has absolutely nothing to do with mass, so M is 0. It involves a measure of distance, giving us length to the power of 1, and it's divided by time squared, which translates mathematically to t to the power of -2. Makes total sense, right?
All right, Section 3. Distance versus displacement. Mapping the path.
When we talk about distance, think of it as the exact footprints you leave behind no matter how much you wander around. It's a scalar quantity. That means it simply tallies up every single step you took along your actual path, without caring in the slightest about which direction you were actually facing. Now, in stark contrast to that, displacement is a vector quantity. This means it only cares about the straight line from your initial point to your final destination. It has to have a definite direction. So, if you run a complete lap around a track and finish exactly where you started, your distance traveled might be 400 meters, sure, but your displacement, that's a perfectly flat 0. So the key takeaway here is that speed relies on the total wandering distance, while velocity is strictly bound to that directional, shortest path's displacement. If you're running those laps on the track, your speed is high because you're covering ground, but your average velocity after one complete lap is 0. Why? Because your total displacement is 0. It's a subtle but absolutely crucial distinction.
Moving on to Section 4,
The math of motion, writing sentences in physics.
Now, we all know motion in the real world can be super messy, but we're going to focus on what happens when acceleration is beautifully uniform. Think of an apple freely falling from a tree. When an object accelerates at a constant rate, we can predict its exact behavior using a few core mathematical sentences.
And here they are. These three fundamental equations of motion are the exact sentences you need to calculate motion in a straight line. By plugging in just a few known variables, like initial velocity, which we denote as u, time as t, or constant acceleration as a, you can definitively predict the future of that object. You can instantly find its final velocity or its total displacement. It's literally the predictive power of physics in action. Finally, Section 5, Graphing our progress, visualizing motion.
Let's do another quick pop quiz from the source material to see if you can translate the math into a visual chart. Imagine a graph mapping uniform acceleration over time. If you shade in the block of space directly underneath that plotted line, what physical quantity does that shaded area actually represent?
Yup, it's the change in velocity. The area under that graph perfectly calculates the total change in velocity. Since the vertical axis is acceleration and the horizontal axis is time, visually multiplying them together by finding the area brings us right back to velocity. And honestly, this just brings everything full circle. Every single element of a graph translates directly back into our core derived quantities. A steeper slope on a displacement time graph, that means higher velocity. A steeper slope on a velocity time graph, you guessed it, greater acceleration. It's this perfect visual loop of everything we've unpacked today. So as we wrap up this explainer, I want to leave you to wonder about the extreme edges of classical physics, out there where these foundational blocks might actually start to bend. We've mastered the basic alphabet, the grammar of dimensions, and the sentences of constant motion. But what exactly happens to displacement, velocity, and time when an object accelerates closer and closer to the speed of light? I highly encourage you to keep questioning those fundamental limits of the physical world. Thanks so much for learning with me today.